Okay, in this video we're going to be making an improved linear queue. So the problems that we faced before with this were that we would run out of space. So our queue that we made right at the start, our just standard first in first out queue, when we filled it, we would be in a position like this. The front pointer would point to the front of the queue, and then our rear pointer would point to the next available space. In this case, because we've got an array of 8 things here, we have got a full array, so it's pointing to nothing because there's no array space there. And what would happen is, as we dequeued things from the queue, the front pointer would move back, move back, and move back. And it would continue to move back until the front pointer and rear pointer are in the same location. And it meant that we couldn't reuse these positions. So it wasn't a very efficient way of creating a queue. So that's why we went on to make a circular queue, which then the rear pointer would jump round to the front. It would make use of those positions again. What we're going to look at today is the way that we can change it so we can improve our standard linear queue rather than making a circular one, because we've made a circular one already. And we can make good use of our memory locations. And the way we're going to do that is we're going to have our front pointer point to the front of our array, and then when we dequeue something, we're going to shift all the contents of our array over. So you see here, if we dequeue A, we are going to put B into where A was, C into where B was, D into where C was, E into where D was, F into where E was, G into where F is, H into where G was, shifting them up. So we can make full use of this array. And it would continue like that. The front pointer stays at the front, and the rear pointer is going to decrement when we are removing, as well as shifting all of the contents up by 1. So with our circular queues, they also made good efficient use of memory. They were very efficient with memory because they reused the old parts, not like our original queue that we made, which once that front pointer moved on, meant that we couldn't reuse these positions again. So that's why we're bothering to look into this. Also interestingly, the circular queue was very efficient in adding and removing. So regardless of how large or small the array would be, the circular queue would take the same amount of time to add and delete. So we're going to refer to that as being O1. So regardless of the size of it, whether it was 10 million things in it or it just had one thing in it, it was an array of 1 or an array of 10 or an array of 10 million, to add to the queue, you just put the data where the rear pointer is and increment the rear pointer. It doesn't get affected by the size of the array. And the same with removing. You just take a copy where the front pointer is and then move the front pointer up. And our poor queue also worked that way. The one that didn't reuse these places. So they're quite efficient in terms of time. This one, however, we're forcing it to be efficient with memory by just shifting everything down, so we keep our front here. It almost looks more like a traditional queue. when you're in a supermarket or waiting in line somewhere, the front stays where it is and the rest of the people move up. So it does kind of make more sense, this one. And it carries on and carries on and carries on until the front pointer is there and the rear pointer is there. And then front pointer and rear pointer at the same location, it's empty. So this one kind of makes a lot more sense than just moving pointers around, shifting everyone up. However, shifting everyone up, not always a great idea, and it will lead us to have a poor efficiency of n. This big O notation describing the efficiency of the algorithm. Why is it Ln rather than not just O1? Well, the worst case scenario is that we're having to shift every element. Every element's having to shift up. So if you think about how long it takes to shift one element, when we're shifting 8, roughly, obviously it's all dependent on CPU architecture and other things that are going on, but roughly it'd be 8 times as long. And if we had 1,000 items, there'd be 1,000 switches, so it'd be 1,000 times as long. If we had 10 million 10 million things in our array, and we're shifting all of those, it would take 10 million of those switches. That's switching up, shifting up. Whereas if we had 10 million and it was a circular queue, it would still be about moving one pointer, inserting an item, not having to shift the rest of the data. So it's not having to shift all of the elements. So this isn't a very efficient queue. So we're covering it because you get to see a different way of implementing a queue, and we get to talk about this efficiency a bit. So yeah, having to shift potentially, hundreds of thousands of items or millions of items, it's going to have an impact on performance. Whereas just using pointers to move and insert, or move and or copy and then move, it doesn't really matter about the size of the array. It's still going to take the same amount of time. So this linear queue here that we're going to have things shifting to enter data, well, it's still going to just enter the data where the rear pointer is and then shift the rear pointer up. So a second. So adding to this queue is still O1. Adding to the queue, the efficiency is still O1 because it doesn't matter the size of the list, it will still do that in the same amount of time. But removing, dequeuing, you're taking a copy from the front and then shifting every other element down. So that process of, if we've got 8 items, as we've got in this example, or we've got 16 items, when it's doing 16 items, it's going to take longer to shift than when it had 8 items. So what we're going to make use of in this video, so we're going to see again inheritance and polymorphism, the ability to redefine methods for derived classes. So we've got our Q class that we made before. We've still got our access modifiers as protected. I think we also did that one as well. And the queue itself. We've got the on queue and dequeue are public. The peak is public, the size is public, the empty is private, and the is full is protected from our work with the circular queues. So remind ourselves what protected is. Well, protected means that it's essentially private, except it can be accessed via the derived class, the child class, the subclass, all the different names that we had for those. We can access all of these except isEmpty because that's still private. But for our new queue where we're just shifting everything up, we're not actually changing the way that we add to the queue, so we're not having to do anything with that. We are having to change DQ, so we'll have to use polymorphism to redefine that method. We're not having to change peak, we're not having to change size, so those can remain exactly as they are. So now we're starting to see more and more advantages of object-oriented programming. Once you've got a class and you're wanting to create a new one with new methods, new behaviors, it's very easy because you've got lots that you can reuse already. We're not having to do anything with isEmpty, and we're not having to do with anything with isFull. Although we might want to gain access to isEmpty to help us out with this, because we are dequeuing, or we are redefining DQ, so we may want to change that to being protected. So the design for my advanced linear queue, or yeah, we'll keep it without that. I'm going to call it my linear queue. We'll inherit from my queue that we've had before. We don't need any additional properties. We do need to use polymorphism to redefine DQ. And I've also introduced another method for shift because I've said that that's going to be one of the elements that we've got to do in this. But I've kept it as private so that we can only access it from within this class. Okay, so we're going to continue creating our queues all in the same project, so we've got them all in one place to look at later on. So we're going to add a new item, and we're going to call it my linear queue. And my linear queue, well, it's got no properties, so we're not going to have any of those, but we're going to have a constructor. And we're also inheriting, so we have to have the colon and then the class we're inheriting from, in this case my queue. Our constructor needs to be public, it needs to be the same name as the class, and because we're making a queue from my queue, we'll need to pass in a value for size. So it goes and constructs the my queue class too. We don't have to put anything in this constructor because we've got no values that we're keeping track of, and nothing else to construct. It's really that we need to construct the base class my queue with a particular size. So that's the constructor, and then we're going to have the methods. So the methods, we're going to have public override. Now, we previously in a video overrided the DQ method, so we didn't have to go back and type virtual anymore. We can just use that, and we'll come back to that in a second. Our other method that we said we were going to have was a private procedure to shift the values. Okay. I think one more thing we said in the original queue, in my queue, we were going to change isEmpty from being private to protected so that we can access it from the derived class, the child class, the subclass, linear queue. Okay. Now our DQ is going to be quite different from the original. So we're not going to have it call the base class anymore. We're not going to have it call the base class. We're going to just code it entirely new. So our polymorphism here is that if we are a class of linear queue, it's going to do this DQ rather than the parent one. Because we're not doing base.dq, we are not going to be calling the parent one either, the super one. So first of all, if we're doing it in a very similar way, we can have my queue open and we can look at it at the same time. We can check what we had in DQ originally. So when we had our DQ, we first checked whether it was empty. We need to be doing the same thing again. In fact, we could copy that and paste it here. So we're still having to check whether the queue is empty. However, once we get the queue contents at the front pointer, we are not going to be incrementing the front pointer. Remember, looking at our example, we kept our front pointer at 0. The front pointer remained there, and we just shifted everything else up. So the front pointer remains at 0, and then we need to shift the rest. I'm just going to call that subroutine that we made. Although it doesn't do anything yet, I'm just keeping in mind what we have to do. And once we've shifted everything, we can return the value temp, which was what we were pointed to initially. So we take a copy of what the front pointer is looking at, shift everything up, and then return that copy. Now the shifting everything up, space, we need position 0 to get what was in position 1, position 1 to get what was in position 2, position 2 to get what was in position 3. We're doing a lot of repetition. We're going to have a for loop. And it's going to go around the length of the queue minus 1. Because we don't at the end want to have array position. So we're going to use the example of an array that's 8 in length. Array position 7. Array position 7 doesn't want to get array position 8 because array position 8 doesn't exist, and we'd have an error with that. So we've taken another one off. So we're going to the length. We're going to be less than the length minus 1, and the queue contents at position I is going to equal the queue contents at position I plus 1. We're going to take what's to the right of our queue and move it one forward, one forward, one forward, one forward, one forward, one forward. And that's how we're going to do our shift. After the shift is done, of course, the rear pointer is in a different location, so the rear pointer is going to decrement. So it's going to move down by 1. So as we picture a queue that we've been in the past for a shop, we've got the queue, and as someone leaves the front of it, everyone else shifts up. So would the rear pointer. The pointers at the end of the queue would also shift up. So that's why we're doing that there. And that should be it. The linear queue. We've got a constructor to declare the size. We've got our DQ method. We check if it's empty first of all. take a copy of the front pointer, shift everything up, move the rear pointer, decrement the rear pointer by 1, and this shifting is all done in a for loop to move contents from one position beyond into the one before it. Okay, so we're going to follow our testing the way we did with our circular and general queue test. We're going to make a new static procedure. Queue test, linear queue test. And in here, as we go through it, we're going to comment if we expect any form of output and what output we expect. So first of all, we need to declare what it is. So it's my linear queue. We call it linear queue. Set it equal to my linear queue, and we're going to stick with 8 as a size for testing purposes. And then it's what we're going to do next. So we can do a console write line, DQ without the capital there, DQ number 1. So we're going to first of all test the DQ out immediately. The queue should be empty at this point, we've just declared it, there's nothing in it. We would then expect our DQ to give us back an error, some form of underflow. Because there's nothing in queue as it stands. Then we can try and put some things in. So DQ is one we need to test a lot of because in our linear queue, that's one of the things that we've added into it. We've changed the DQ. We shouldn't have to change peak, on queue, and size as much because they are already in this class. They're already in our parent class, and we've tested those, and we've also tested them in our circular queue as well. So we're expecting a lot of this to already work, so our testing doesn't have to be as thorough as we did in the past. We still will do a couple of tests just to make sure that we're still getting the right results, but we're not going to do as many, so we'll just do one size one here. Linear queue dot size, and we expect the output to be 0 because there's nothing in our queue. We're going to unqueue some various different characters. So I'll try and do it a little bit quicker. Copy. So 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to unqueue A, B, C, D, E, F, G, H, and I. We're not expecting any outputs apart from on the I, because that's where we've got 1, 2, 3, 4, 5, 6, 7, 8 characters have been added with the H, and 9 would make an overflow because it's full. So we expect an overflow there. We can test for the size again. We're not going to do too many of these, but we'll test for the size before the H. So size 2. We will expect it to be 7. Okay, and then we really need to get to the dequeuing. The dequeuing is going to be the more important thing for us. So copied what the DQ was before, so DQ2. We expect A to come out first. This is a first in, first out data structure. we'd expect A to come out first, B to come out second, DQ3, and so on and so on and so on. Okay, so C would be after that, D, E, F, G, and one more would be H. One more after that would be an error, and it would again be error underflow. I'll just change these numbers so they all make sense. DQ4, DQ5, DQ6, DQ7, DQ8, DQ9, DQ10. Is that correct? So we've got one DQ there. A, B, C, D, E, F, G, H, and then I. Yeah, as we're testing for errors. We should of course try and put at least one peak in here just to show you that that still does work, but because we didn't change it, we shouldn't have any issues there. It's one of the advantages of using object-oriented programming. Once you've got a class that does something and you test it and it works, I suppose it doesn't have to be a class, it could be any method, any subroutine you want. Once you've got a subroutine that does what you want and you've tested it and you're happy that it works, you can not always presume, because some things work differently when you introduce new bits to them, but you can certainly be fairly confident that it's going to work. So we don't have to do a vast amount of testing of that. And if we're peaking, we'd expect it to have D, because the next thing to come off the queue we said was going to be D. What else? I think I'm fairly happy with that set of tests. So we're expecting error underflow, 0 to be output, no outputs when we're inputting, 7 because we've put a size check there, an error overflow because we've tried to add too many things to the queue, and we're expecting A, B, C, D because that was the order they came in, the first in, first out. We're expecting 2 Ds because we tried to peak, which shouldn't DQ, it should just give us the result D, and then when we DQ D we should get D as well. E, F, G, H, and an error because we've underflowed and there's nothing left in our queue. So give this a test, a run. See what we get. Of course, do not forget to actually call your subroutine that you're going to use to test. So linear key test there, we'll call it, and you can see it's got a reference now. I'll take it back out again. So if you're unsure about why some of your code's not running, first place to check is, are you actually running the code? And Visual Studio here shows us that there's no references, so we're not actually ever calling that subroutine. So let's call that subroutine now. So linear queue test, and you see here reference 1 pops up. It allows you to jump straight to wherever you call it, in this case just a few lines above. Now when we run it, we do get some outputs, and let's check against what we were expecting to come out. So we expected an underflow error at first, we got that. We expected the size to be 0, then we added 7 items and we expected the size to be 7, it was. The next thing, we expected an overflow error. Then we DQ A, B, C, it worked exactly the same. We peaked D. Yes, we DQ'd D, E, F, G, H, and then we got another error for underflow, exactly as intended. But we want to see that shift happening. We want to see that it does actually shift forward and back and stuff. And I suppose we could have done this set of tests with the regular queue. The point was that we could reuse those positions. So I'm going to copy A, B, and C on queues, and we're going to queue up A, B, and C again. In fact, we're going to do that before we get to G. So I'm going to queue up A, B, and C. So we're going to, that will show us that we've used more than 8 positions in total. We've dequeued some of the stuff, so we're not using all more than 8 in one go, but it'll show us being able to reuse those. So what's going to happen? A, B, C will come out, C, D, E, F will come out. We are going to put A, B, C in. So A will be stored after the G and the H. So our contents at this point, the contents of our array at this point would be G, H, A, B, C. Okay, we'll no longer get an error here because that should output A. And we'll just do a few more dequeues to get to the point where we're empty again. So dequeue A, dequeue B, dequeue C, error, underflow. Let's run this. And then what we'll do is put a breakpoint in and see the shifting in action. Make sure we're confident with the idea and what we've produced here. So concentrating on this last bit, so G, H get dequeued, A, B, C get dequeued, and it's an underflow error. Excellent. It's always nice when it goes the way you expected. So what we're going to do is put a breakpoint in and see it in action. So we will look at when we dequeue the F, for example. So it'll have done some stuff before this point, and we're going to see what happens when we dequeue F. So we start the program, breakpoint, clicking this left-hand side here, put in a little red stop mark, allows us to go through the code, and then you can press F11 or this button up here to step through. So it calls the dequeue. Is it empty? It calls is empty. The front pointer at the moment is 0, the rear pointer is 3, so they are not equal. So it returns false. So it doesn't do that if statement. And the front pointer is 0. We get a chance to look at our queue. Our queue's got F, G, H, and then a load of H's. Why has it got those H's? Well, it's just not, when it's doing the shifting and the copying, it's just copying all of the last ones over. And we've never actually got rid of or deleted the last one. We could go and do that in a second. And then the shifting. So we've taken the F, we've taken a copy of the F, and then we're looking for that queue to shift up. So we should get G, H, and then a load of H's. So initial position, we run that, and G has been copied from position 1 to position 0. Next up, H should be copied from 2 to position 1. Goes round, and let's see that happen. Yes, the H has gone from position 2 to position 1. And continue, and it works. Just to make it look nicer when we actually do our actually get to see what our queue looks like, we can make sure that we eliminate the last thing in the queue, so it looks empty when it's after us. So the queue content dot length -1 is going to be our last position in the array, and we can set that to just being blank. So if we run it again, we've still got the breakpoint in. So let's just step into what we've got going on. Still not empty. And we shift. Now our queue contents, we've got those blank spaces at the back instead of just copies of H. So after this shift happens, the F won't be here and the G and the H will be moved up in the queue, or moved up in the array. See that now? Almost there. So our queue's now just got G and H in it, and the rest of the spots are just blank spaces. So we can follow it through and see what happens when we try and DQ next. So between DQ7 and DQ8, we've unqueued A, B, and C. So we've left off with our queue containing G and H. A is going to be put on, B is going to be put on, C is going to be put on. We'll carry on and then see it in action. So it's not empty, the front pointer is 0, the rear pointer is 5. And just hovering over the variables tells you what they are as well. If you're wondering what I'm doing, not doing anything special, just hovering it over, it's telling me it's 0. So the temporary char is just the G, and then we're going to go and shift. So the queue contains G, H, A, B, and C, and what will happen, it will shift, so the queue will contain H, A, B, C, where H is at position 1. And that's what the shift is going and doing. Skipped forward, there's the H, A, B, C. So the shifting is working. And the rear pointer's pointing to position 4. Well, let's look at position 4 on the queue. That's the next empty space. That's the space behind C. So that's pointing to the right location. And we get exactly what we're looking for. So that's the linear queue where we shift all of the values up by 1. More of a traditional looking queue that you get in real life, where you're queuing for a till at a shop. You're in the queue, and as people leave the queue, the whole queue shifts forward. It's a more traditional thought of it. But as we mentioned earlier, it is less efficient at dequeuing because of this shift that we've got going on. The shift making it so that as our queue array expands, gets bigger, if we have a much larger array, the time it takes to do this shifting takes longer. So it's efficient, more efficient with memory than our just generic queue where we didn't reuse array positions, but it's not as good with time, because as our queue array expands, the amount of times this would have to go around increases. So the amount of time that the CPU takes to process this method would increase.